1. Structural systems explained. Frame versus shear versus core. Structural systems are the backbone of architectural design. They determine how a building carries loads, resists forces, and maintains stability. Understanding structural systems allows architects to design buildings that are both expressive and safe. Frame structures consist of beams and columns that carry vertical loads. They provide flexibility in planning and are commonly used in low to mid-rise buildings. Frames allow open floor plans, but require additional systems to resist lateral forces. Shear wall systems use vertical walls to resist horizontal forces, such as wind and earthquakes. These walls increase stiffness and reduce building movement. Shear walls are often integrated into staircases or service areas to minimize spatial disruption. Core systems rely on a rigid central core that resists lateral forces and supports vertical loads. The core typically houses elevators, stairs, and services. This system is highly efficient for tall buildings. Each system responds differently to gravity and lateral loads. Frame systems prioritize flexibility, shear walls prioritize stiffness, and core systems prioritize efficiency at height. Most contemporary buildings combine these systems. Architects must understand structural logic to collaborate effectively with engineers. Structural decisions influence form, space planning, cost, and long-term performance. 2. How tall buildings stand up. Simple structural breakdown. Tall buildings are exposed to extreme forces due to height. Gravity loads act vertically, while wind and seismic forces act horizontally. Structural design focuses on managing these forces safely. Vertical loads include dead load from the building's own weight and live loads from occupants and furniture. These loads travel through columns and walls down to the foundation. Lateral loads are often more critical in tall buildings. Wind causes sway and vibration, while earthquakes produce dynamic forces. Buildings must resist these movements without discomfort or failure. Structural strategies, such as cores, brace frames, and tube systems are used to manage lateral forces. Outrigger systems connect the core to perimeter columns, increasing stiffness. Foundations play a crucial role in tall building stability. Piles and raft foundations transfer loads deep into the ground where soil conditions are stable. Tall buildings do not aim to be rigid. They're designed to move within safe limits. Controlled flexibility ensures safety, comfort, and durability. 3. Construction phases explained. From excavation to finish. Construction is a sequential process that transforms design into reality. Each phase builds upon the previous one and requires careful coordination. The process begins with site preparation. This includes clearing, excavation, and soil stabilization. Errors at this stage can affect the entire building. Substructure construction follows, including foundations and basements. These elements support the entire structure and must be executed accurately. The superstructure phase involves constructing columns, beams, slabs, and walls. Buildings typically rise floor by floor in a repetitive sequence. Once the structure is complete, enclosure and services are installed. This includes facades, mechanical systems, electrical wiring, and plumbing. The final phase involves finishes, landscaping, and commissioning. At this stage, the building becomes usable and ready for occupancy. 4. Materials and architecture. When and why to use each. Material choice is both a technical and design decision. Materials influence structure, appearance, durability, and sustainability. Concrete is widely used for its strength and fire resistance. It allows complex forms and provides thermal mass, but has high environmental impact. Steel offers high strength with relatively low weight. It enables long spans and fast construction, but requires protection from fire and corrosion. Timber is a renewable material with warm, aesthetic qualities. Engineered timber allows larger spans and is increasingly used in sustainable construction. Material selection depends on climate, structural role, cost, and availability. No material is universally better than others. Architects must understand material behavior to design responsibly and collaborate effectively with engineers and contractors. 5. Passive design strategies explained. Light, air, and heat. Passive design reduces energy consumption by responding to climate. It focuses on using natural resources efficiently. Daylighting reduces the need for artificial lighting. Proper orientation and window design improve visual comfort and energy performance. Natural ventilation uses wind and temperature differences to cool buildings. Cross-ventilation and stack effect are common strategies. Thermal control is achieved through shading, insulation, and thermal mass. These strategies reduce heat gain and loss. Passive design improves comfort while lowering operational costs. It is most effective when integrated early in the design process. Sustainable architecture begins with passive strategies before relying on mechanical systems. 6. The future of architecture. Smart cities, AI, and sustainability. Architecture is evolving in response to technological and environmental challenges. Future buildings must be adaptive and efficient. Smart buildings use sensors and automation to optimize energy use and comfort. Data-driven systems allow real-time monitoring. Artificial intelligence is changing design processes. AI assists with optimization, simulation, and generative design. Urban challenges such as climate change and population growth require innovative solutions. Architects must think at the city scale. Sustainability will define future architectural practice. Resource efficiency and resilience are no longer optional. The architect of the future designs not just buildings, but integrated systems that support life and environment.